Kevin and Peter will present how Multimatic replicated real-world subjective testing environments through the implementation of high-fidelity correlated vehicle road models and simulator motion queuing analysis using the DiM250 driving simulator.
Thank you, everyone. So a little bit about Multimatic. For those that don't know, so Multimatic is a supplier that delivers manufactured products and engineering services to the global automotive industry. We are headquartered in Toronto, Canada, with facilities in North America, Europe, and Asia. Here's just a small subset of some of the products that we've worked on, and we go everywhere from low volume production all the way to high volume components and projects. So Kevin and I fall under Multimatic Engineering. So we deliver integrated design, analyses, prototype testing for products ranging from individual components to full vehicle programs. So Multimatic has quite a long-standing history with VI Grade and driver-in-the-loop simulators. So in 2011, we installed the driver-in-the-loop VI Grade simulator at the Multimatic Technical Center in Toronto, Canada. In 2019, we installed a DIL in our UK office. And in 2021, together with VI Grade, we installed a DiM250 at the Detroit Sim Center in Novi, Michigan. So a little bit about the Multimatic Integrated Systems Analysis, or MISA approach. It's an approach that we apply throughout the company, and it allows for the translation of vehicle-level design briefs into components that achieves those goals. And our driving simulator fleet at this point is a critical part of that process and an extension of it. So the DIL and the DIM validation bridges the gap, but it's true, between the analytical and the subjective, and integrates the driver into our MISA process. And in some cases, this has allowed us to reduce the total development timelines by over 50%. So what are the goals of our DiM Ride project? So we want to expand the virtual ride quality subjective assessment using our VI Grade DiM250. And how do we do that? So we've replicated real-world subjective testing environments through high-fidelity correlated vehicle models and our simulator motion queuing analyses. And these developments allow for the virtual assessment of subjective ride performance, saving, obviously, time and providing a link between objective metrics and subjective evaluations. And obviously, when we talk about ride, we're talking about the response of the vehicle body to road disturbances in the 1 to 30 hertz range. Here's a little kind of snapshot of a couple of quotes during this development process that we've gone through from Murray White, our technical director and test driver in vehicle development. So initially, we were not able to feel the difference between the different damper settings on the DiM. We spent a lot of time working on correlating the models. We got to the point where we were able to discern the different damper modes blindly, and here he's referring to our adaptive damping technology that we provide for our vehicles. And currently, 100% of the changes we make on the DiM are directionally replicated on the real vehicle. So we've come a long way, and how have we done that? So in order to achieve the goals that we just talked about, we have 3 pillars that are going to contribute to that: virtual vehicle model, the virtual road model, and motion platform queuing, obviously. So for the virtual vehicle model, I think people in this room, we don't need to go into too much detail, but one slide doesn't really do it justice. But a high-fidelity virtual model is critical to the ride development program, or any program for that matter. And some of the core competencies and processes that we use include suspension kinematic and compliance development, aero development, tire model integration, and all kinds of control system integration. Obviously, a model is only as good as it can be correlated to the real world. So we use objective testing methods to make sure that those models reflect the real vehicles. And some of the testing that we use to do that are 4-post, K&C testing, and obviously road and track testing. In the virtual road model area here, so high-fidelity virtual road models are critical for replicating tire-to-road interaction and simulation. And they play, again, a critical role in our subjective ride assessment. So we've developed methods to process laser scan point clouds of all kinds of things, all kinds of tracks, public roads, proving grounds, and obstacles as well. So laser scanning technology has come a long way. We have scanning techniques that can measure 10,000 plus points per square meter, typically more than 100 million points in an individual scan. And this involves an instrumented vehicle that scans the road surface and the surrounding environment. So at a high level, in order for us to, when we generate a track model, what are we doing? We're removing the scenery points and points that are not relevant to the road surface that we're interested in modeling. We remove spurious overhanging points like trees, overpasses, if a bird flew by, pedestrian walkways, all kinds of things. We create a uniformly spaced grid. We map the z-coordinates of that grid onto the surface. And then we can apply a low-pass filter in order to have the content that we require within the road. And we end up with a ribbon mesh of the actual road surface itself. In parallel to that, we're also creating a mesh of the surrounding environment. We combine these two together, and we're ready to drive in the virtual world on the model that we created. So obviously, again, correlation is one of the most important factors here. So ensuring that the virtual road model has all the same content as the road it represents is critical to make sure that we have something that is going to give us good information. So we use offline simulations that we conduct with a correlated vehicle model driving over the generated road model. And then we take that same exact vehicle and drive over that same exact road in the real world. And we compare those results to assess our model's fidelity. So here we have an example of some of the road model development we've done. So in black, we have the real measured on-car data for that road. In blue, we have a baseline road, and in red, we have an updated road. And some of the knobs that we can turn when we're developing these roads is the element density of the mesh itself, and also the low-pass filter cutoff. And so here we have a bunch of PSDs that are showing the difference in correlation to the real road. All kinds of things such as acceleration, gyro from the IMU, X and Y, the hub accelerations, and body accelerations. And obviously, these are PSD plots in the frequency domain. So you can see that the red road, the updated road, or the higher fidelity road from the laser scan improves chassis heave, pitch, and roll in the 7 to 20 hertz range. In 12 to 14 hertz, it's a significant improvement. So we can see how the techniques we use to develop these. We've got a full suite of roads that we've scanned in Michigan that we use for subjective and ride quality evaluation in the real world, and we've replicated that now in the virtual environment. And some of the next steps we're looking into is VI Grade's relatively new grid mesh RDF road format that's going to hopefully allow us to eliminate the element density limitations that we have right now with road meshes to run live on the simulator. And this allows for resolutions down to 1 centimeter. And it's really critical to capturing things like cracks in the road, railroad tracks you may drive over, any small imperfections that some of a coarser mesh would maybe not necessarily replicate 100%. So now I'm going to hand it over to Kevin, and he'll go over the motion platform queuing.
Yeah, so the third pillar of the project was to work on the motion platform queuing. It's critical to reproduce accurate driver fields on the driving simulator in order to fully exploit the driving experience. There is two components of it. There is a software where there is an algorithm which compute the platform displacements by transforming the vehicle state from the simulations into perceived acceleration for the driver model. And we have been using VI Drive Sim software, which allow you to refine the filling and the queuing to your particular applications by changing over 150 coefficients. And there is a hardware component, which is a DiM250, which we have been using at the Detroit Sim Center. And Multimatic being involved in many projects, we have been built a fully reconfigurable cockpit. The advantage of this cockpit, it allows us to replicate the real car driving positions by interactive and changing components and locations, such as seatings, pedals, steerings, as well as the roof, pillars, and bodywork. We also instrumented our DiM250 with additional sensors, which allows us to close the loop and ensure correlations between our vehicle models, but also the real car and the motion platform and the queuing that we provide to the driver. And thanks to our vehicle models, but our platform response and the high fidelity of it, which we are working well up to a region of 20 Hz, as you can see on most of the current plot at the bottom, we were confident that it was a good environment to do our right project performance testing. One of the main knowledge we've learned during this process was understanding which of the queuing coefficients need to be adjusted to perceive and get accurate driver feedback. As we mentioned earlier, motion queuing can change the perception of the driver for the same vehicle. And we found in our applications and make the initial assessment that we need to amplify the vertical degree of freedoms to do our right developments. But then once we align all the degree of freedoms in both vertical, roll, and pitch, we proved that our driver was able to provide feedback not only on the verticals, but also on the roll and the right performance of any given set of changes. The other important aspect that we found in our motion queuings was ensuring our amplitude ratio between our model and our simulations was maintained through the frequency and the range, not creating different modes or non-existing modes on the vehicles, whether from the body or the wheel mode, which were not present, which we provide wrong cues to the drivers. Once we are able to validate our vehicle models and ensuring we have adequate and optimal vehicle settings, we are able to apply it from actual applications. And here we have an example where we'll speak about a case study where we tested our adaptive damper on a real car driving around one of the ride roads in Michigan. We have our car data in black and our vehicle model in colors. And we compare sensor data equipped on the accelerometers and gyro on both setups, and validate them, they were correct in aligning up properly. Next, we are able to use this tool as settings and evaluate different damping modes between adaptive, passive, as we are showing here. And in this case, we have the rear car on the left and our DiM platform, so the actual platform motion on the right, not the vehicle model. And we are looking at a comparison between passive mode and an adaptive mode in color. And in both cases, we can see the influence of the damper change is replicated on both the real environments and the virtual environments, ensuring that the driver was able to provide feedback and even blindly detect which setups was on the car. Once we have obviously high fidelity and vehicle models, we are able to go even further and use this technology to provide more subtle changes on one axle at a time, or compression ratio, compression to rebound ratio, a different software of our damper and adaptive technology in order to fine-tune. And in most 100% of the times, this replicates in the real world. So that means any testing and development we are doing on the simulator will translate in a real vehicle. One of the tools we have been conveniently using is our offline simulations, which we are able to predict and optimize and validate motion queuings and our models, vehicle model and road models, prior to running a DiM simulations. And then the last step is to put the driver in the loop, saving us a lot of the times in the process. So in recent months, we have been using our driver in motions very intensively for all the ride performance project we've been involved. And effectively, there are 3 vehicles we equipped with our adaptive damper technologies have been modeled and run on the DiM250 in Novi, at the Detroit Sim Center. The next step for us will be to bridge the gap between our primary ride and NVH in order to enhance and increase the range of simulations. And for this, we are planning to work on more higher fidelity models to improve our road and tire modeling interactions. We started working towards implementing a new road mesh, as Peter mentioned, but also multi-point tire models, as well as audible cues for the driver, which have been important in terms of ride evaluations, particularly in the terms of secondary ride and harshness. Thank you for your attention.